Hello, everyone. My name is Nida Itrat Abbasi, and I'm a second-year PhD student at the Department of Computer Science and Technology at the University of Cambridge. I'm here to present my work on child facial expression recognition. I will be very happy to answer any questions via email, and I will be present virtually as well as physically to discuss any comments or feedback that you may have with regards to this work. So let us begin. The title of my work is Statistical, Spectral, and Graph Representations for Video-Based Facial Expression Recognition in Children. Child facial expression recognition is a relatively less investigated field in the whole realm of affective computing. But why measure facial expressions in the first place? The human face is a rich and reliable resource to understand complex cognitive processes, and we rely on it extensively, not just for human-human communication, say for pain detection, but also in human-agent interaction to understand engagement and interests. For population groups that do not have very advanced verbal communication abilities, like children, it can help us understand some nonverbal behaviors as well. However, there are very few machine learning-based facial expression classification approaches that have been specifically developed for children. And we believe this is a valuable stepping stone for future child-agent interaction technologies. Why construct child-specific facial expression frameworks? There has been a lot of work that has been done on facial expression recognition, but the models that are trained on adults do not generalize very well on children. And the reason for that is that the facial expressions of children are very different from their adult counterparts. They're often exaggerated, unique, as well as at times incomplete. Moreover, child facial expressions are very dependent on demographic factors such as gender, age, and ethnicity. The novelty of our proposed approach is that it's the first approach that constructs video-level heterogeneous graph representations for facial expression recognition in children. Secondly, it's the first approach that predicts children's facial expressions using the automatically detected action units. What are the advantages of using facial action units? They provide an objective and descriptive representation for measuring facial behavior changes, as well as for vulnerable population groups. They provide an ethical advantage over using raw images and videos, as these raw images and videos can be discarded in real time once AU detection has been performed. Our proposed methodology consists of the following steps. The first step is frame-level facial behavior modeling. As I mentioned in the previous slide, we used OpenFace Toolkit to extract the intensity and occurrence of 17 AUs, namely AU1, 2, 4, 5, 6, 7, 9, 10, 12, 14, 15, 17, 20, 23, 25, 26, and 45. So at the end of this step, we had a 34-channel time series. So it was 34 channels across the length of the video segment. The second step is video-level facial behavior modeling. In this particular step, we constructed 3 representations: statistical representation, spectral representation, and graph representation. In this slide, I'm going to go in detail about statistical and spectral representation, while in the subsequent slide, I'll talk more about the graph representation. So for statistical representation, we extracted 24 statistical features named from the AU time series, namely the mean, the median, the standard deviation, and the maximum. followed by the first order derivatives, the mean, median, standard deviation, and the maximum, and then the second order derivatives, mean, median, standard deviation, and maximum. For the statistical representation actually does not give us any information about temporal dynamics, that is the evolution of AUs over time. So for this particular purpose, we constructed spectral representation as well. So the AU time series was converted to a spectral signal using a Fourier transform, where each component in the spectral signal corresponds to the intensity of a unique video level frequency. Then for all the video clips, we extracted the K common frequencies, making this approach length independent as well. We did feature ranking using correlations where we selected the top D features that have the highest correlation with the expressions. And we fed this into the BioLSTM model. So how we did this is we treated each feature as an individual step to be fed into the BioLSTM model. This way, the BioLSTM model would adjust its forget gate on the basis of the importance of the input features. In comparison to standard classifiers such as support vector machines and multilayer perceptrons that equally consider all features at the input level, the proposed strategy treats these features differently based on their correlation with the children's facial expressions. Specifically, the BioLSTM model would first learn the features with lower correlations and then learn the most informative features at the last step, allowing the model to emphasize the most important features and forget the less informative ones. Now, regarding the graph representation, while the statistical representation and the spectral representation provide rich information about the temporal dynamics and some of the static information, it does not give us the spatiotemporal details at each timestamp. So for this particular purpose, we first constructed a spatial graph representing the static AU status of each frame, where all the AUs were the vertices, and they were given a value of 1 if the AUs were activated, or 0 if they were not activated. Then we combined all the spatial graphs for all the frames in that particular video. This way, we got the frame level AU activation status, as well as the AU activation duration and the dynamics. We fed this into a well-trained graph attention network so that we could get the video level heterogeneous representation. We conducted our experiments on the LYRIS Children's Spontaneous Facial Expression video database that contains video clips of 12 children of different ages, gender, and ethnicities. There were about 208 video clips. As compared to previous databases, the LYRIS database contains videos of spontaneous expressions of children and not posed or static images. Now, the training details, we excluded videos that belong to the anger class because they weren't sufficient in number. There were also certain video clips that had combined categories like happy surprise, sad fear, so we excluded those as well, and some clips that were a very short duration, but in total they were less than 3% of the files. We conducted 12-fold leave one child out cross-validation, where in each fold we trained the model on 11 subjects and we tested it on the 12th subject, and this process was repeated 12 times over. For training the BioLSTM model, we used cross entropy as the loss function and Adam as an optimizer. And the learning rate, I hope, are visible on the slide. We also compared this with the standardized MLP models. And the results are as follows. Comparison between video level representations. So as you can see, the combined representation provides us with the highest accuracy in MLP and even higher in BioLSTM. Comparison between MLP and the proposed BioLSTM model. So the BioLSTM model actually outperforms MLP in all the representations except for in spectral representation. And comparison between expression classes. If you can see the image on the slide, the positive emotions like happy and surprise are often classified accurately, while the negative emotions like disgust and fear are often misclassified. But I would like to bring your attention to subpart D of this particular figure. As you can see, disgust is often misclassified in all the representations. However, in the combined representation, it is classified accurately for some of the video clips. The conclusions are that we propose the usage of statistical, spectral, and graph representations to encode multi-level facial behaviors for video-based child facial expression recognition. We find that the combination of all the three representations using the BioLSTM model provides the highest accuracy, and models that are developed in this particular work, we hope will provide a valuable stepping stone for future child-agent interaction research. Our future work entails using more advanced deep learning frameworks like gated graph convolutional networks and other end-to-end network architectures for further improving the accuracy of our models. The authors would like to thank all the supporting and granting agencies that helped and supported this particular work. And as mentioned in the beginning of this presentation, I will be very happy to answer any questions via email. Thank you so much for your attention, and I look forward to your questions.